This lecture is about stochastic variables. A stochastic variable is a mapping from the event space, here denoted omega, to a point on the real line, x1 in this case. An example would be a die. So before I roll the die, I have it in the abstract notion of a die which outcome is not known. After I roll the die, I get a number of realizations, 1, 3, 5, and so forth. Each time I roll the die, I observe a new realizations. So the stochastic variable is the abstract notion of the die being rolled, whereas the actually observed value of the die is the realization. I can view the die as collecting all the possible outcomes together, but when I have rolled the die, I observe the outcome, the observation, the realization, and I see the value of that realization. So after I have observed it, it is not random anymore. Then the number rolled is 3, 5, or whatever. But before I roll it, I still do not know what the value will be, and the value that I will be observing is dictated by probabilities. Another examples would be the temperature. The temperature would be what we will call a continuous stochastic variable. It would take values that are continuous, whereas the die would be a discrete stochastic variable. It will take discrete values only. In this presentation, I will focus on the continuous stochastic variables, but the discrete stochastic variables will behave very similar to those. As noted, the outcome that I can expect the stochastic variable to have are dictated by probabilities. We use the probability distribution function to describe what we are expecting the stochastic variable to take on as values. That is the same thing as saying that what is the probability of the stochastic variable x taking on the value less than, say, little x. So for instance, if we are discussing the temperature, what is the stochastic variable x, which is the temperature outside, for instance, what is the likelihood of that temperature being less than, say, 20 degrees? That is the probability distribution function at this point x. This is the same thing as the integral of the probability density function, which is then, of course, then the derivative of the probability distribution function. The probability distribution function is such that it is a monotonously growing function that then maximizes at 1, the probability of 1 when I have reached the maximum possible outcome. Whereas the probability density function is rather a density telling me where the probability of mass lies. So this outcome here would be the most likely outcome. That is where I have most of the probability distribution centered. To capture this, we normally discuss the expected value of a stochastic variable. That is, what do we think the stochastic variable will take on as a realization on average? So I'm computing the average over all possible realizations. So think of this as the temperature being observed over and over and over and over again in some infinite many different ways for the same time point. Or if we discuss the die, I would roll the die infinitely many times. What on average would I expect the outcome to be? That would be the mean value, the expected value. And that would coincide with this center of mass for the probability density function. Also important is how much do I expect the stochastic variable to vary around this expected value? So if I say that I expect the temperature outside to be, say, 20 degrees, how much do I expect it to vary around that number? So this is measured by the variance, which is then the expected value of the stochastic variable minus its mean squared. If my stochastic variable has a very low spread, that is that the probability density function is very narrowly distributed like this, I expect the variability of the outcome to be very limited. If I redo my observations over and over again, I expect a very similar outcome each time. So say that I'm measuring the temperature in a room where there basically is room temperature control. I expect it to be 20 degrees, then plus minus 1 degree or something very similar each time. Then the variability, the variance of this stochastic variable is low, and the probability density function is then concentrated. Well, on the other hand, if my probability density function is well spread like this, so it has a much wider spread, I expect a much larger variability of the outcome, meaning that if I will look in at the temperature example, I would not have 20 degrees each time. I would have 20 plus minus, say, 10 degrees. So it will vary quite a bit as it would do outdoors over the seasons, for instance. So the expected value and the variance will dictate what I expect my realizations to be and how much they will vary from one realization to another. I can, of course, have two dice that I roll simultaneously. Then I will observe this as a two-dimensional event. So I have, for each time I roll the die, I will get two outcomes. So the stochastic variable here is two-dimensional, not one-dimensional as it was before. So similarly, I could measure the temperature and the air pressure outside. So each time I make an observation, I will get two numbers. So it's a two-dimensional realization. I will denote that by having the stochastic variable z containing two components in it. So the stochastic variable will have a probability density function, which is then three-dimensional. So it will have the x and the y, and then there will be a peak dictating how likely that outcome is. Of course, I can still talk about the expected value. What do I think this two-dimensional variable will be? And I can speak about the variability just as before. The probability density function will then be a function of z, which is then the concatenation of the x and y variables. So that means that the probability that the stochastic variable x is less than this number, little x, and the stochastic variable y would be less than this little y here, which will be the double integral up to x and y of the probability density function, which is now, as I mentioned, a three-dimensional function. It is formed by computing the partial derivatives with respect to x and y of the probability distribution function. Often I also wish to have a notion of how dependent the different variables are to each other. So if it was the temperature and the air pressure outside, how much do they depend on each other? One way, the extreme, would be to say that they're statistically independent, meaning that the probability density functions are separable like this, so I can separate them out completely. That is to say, they have nothing to do with each other. This is a very strong assumption that, strictly speaking, is rarely fulfilled in reality. So let's have, for an example, the number of cats in my garden and the temperature of the dark side of the moon. For all practical purposes, they would be independent. I can view those as being independent. If it gets colder on the dark side of the moon, I see no reason why I would get fewer cats in my garden. However, if you want to be strict about it, if the temperature on the dark side of the moon was extremely hot, obviously that would affect the temperature on Earth and the number of cats in my garden. So they're not truly independent, but for all practical purposes, of course, they are. So we wish to separate what is a theoretical independence and, for all practical purposes, being independent. One way of doing that is to speak about variables being uncorrelated instead. That is the same thing to say that the stochastic expectation separates. This is a much weaker assumption that is also being implied by the variable being statistically independent. If they're independent, they're also uncorrelated, but not the other way around. You can very easily show this by just writing out the integrals and separating them out like this and see that if they are independent, then they will also be uncorrelated. But the other way around does not hold. In order to capture the dependence, we often will speak about the cross covariance between two variables. So for instance, if I'm looking at the stock quotes and the tech stock quotes goes up, if Google goes up, then it will likely affect the Facebook stock quote. So there is a dependency between these two stochastic variables. I measure that by looking at the cross covariance between these stochastic variables, which is the expected value between x and y, subtracting their mean from each other like this. A high cross covariance will then mean that the variables are highly dependent on each other, whereas if the cross covariance is low, it means that there's a little link to it. Often you normalize by the variance of each of these stochastic variables so that you get a correlation coefficient, which is then normalized between 0 and 1. A low value of the correlation coefficient, say 0.01, means that there is no link between these two. So that would be, for a good example, of the number of cats in my garden and the dark side of the moon. Whereas if there is a strong link, say 0.9, then there is a very strong predictability from one of the variables to the other. If I know one of the outcomes, I have a very strong indication what the second outcome would be. Then they're strongly correlated with each other. And of course, then I'm able to exploit that to predict the outcome of the other parameter.